Okay, perfect. Yeah, welcome everyone. Super sad to be not there in person and to connect with you. My name is Fabian. I'm one of the two co-founders of Paretos. Actually, to keep it really brief, been in the research for multi-objective optimization for more than 6 years. Realized that optimization is really great, but in order to bring it into application, there are some caveats. And today, I'm really happy to present together with Robert how to combine predictions, AutoML methods, and multi-objective optimization to really push technical results into application.
Yeah, perfect. My name is Robert Haase. I'm a physicist. I'm focusing for a couple of years on the field of time series forecasting. Also was early investigating into transformer-based methods back in 2019. And it was at that time when I realized the great potential of these methods, especially in this context for time series forecasting. Coming then into the industry, I realized two things. So the first thing is forecasting in the industry is most of the times a highly manual process driven by humans, worked in Excel. Secondly, also we have lots of complex, highly heterogeneous data that we see in the industry. And to basically cope with those 2 points, we at Paretos came up with a solution of how to use AutoML methods of doing time series forecasting efficiently, and besides that, not only focusing on the AutoML optimization part of our models, but also mapping directly some business value on top of that. Since managing complexity and dynamics, we need to find strategies of how we can adapt quickly to new situations that are appearing in the industry. So we need also some dynamic methods in order to cope with those dynamic environments. And therefore, we came up with some AutoML framework that I would like to introduce to you. So really small introduction. So basically, probably you all heard about it, but what time series forecasting is in general about is basically we predict some future observations based on some historical values. This could be some historical data by the target data itself. It could also be some future external data, some sales data that are coming up. And two important industries where it's used quite common is, for example, in the retail industry or in finance industries. There's also logistics that may use it a lot, and where a lot of business value is created. So basically, the framework or the time series framework is quite easy. You have some input data that you put into your model. In this case, for example, just a normal or usual statistical model, and this model produces some time series forecast, and then you have the first forecast based on your customer data. Besides that, obviously, there are more models that we can execute. For example, next to some statistical models, you could also use some machine learning-based models, some tree-based models, as shown in this graphic. Or finally, you could also use some deep learning methods, might it be NLP-based or transformer-based, in order to produce some predictions. And then you have a big zoo of models that are trained which produce a lot of data. These models can then be, by AutoML, for example, be hyperparameter tuned by itself. So you have a bunch of models that are, for example, auto models that are hyper optimized for the common problem. And there's a lot of computation work that needs to be done behind the curtains. And then in the end, in this case, you, for example, get one best performing model which performs the best and performs the best metrics, and then this model is chosen as one global model. Easy. So, as I said in the beginning, in the industry, we're having lots of complex data. So we're having demand data from logistic customers that have up to 2 million SKUs. So each of the SKUs needs to be modeled separately. And this is a lot of data, and this is also a lot of heterogeneous data. So we see that the data itself, they have a lot of different characteristics in one and the same data set, and you need to find some machine learning methods and models that can cope with the whole complexity, the whole diversity of data set within for one given use case. So here we see the Pareto's law, for example. This is just one example that I wanted to show you. So this is a common a distribution of data that we see quite often. For example, we have some smallish amount of products. In this case, it's 20% of the products that hold up to 86% of the volume. This is completely different to, for example, the 60% of the products that hold only up to 4% of the volume. So you see the dynamics and the statistics of the time series data, they can completely change with one data set. Furthermore, we see that, for example, for those 3 segments that I just showed, we have different best performing model architectures, model types, that will need to be trained and executed. So for example, we have this, for this A method with high volume, we have high fluctuation, some external factors that drive the time series to be non-linear on some days. So for example, therefore, machine learning methods or deep learning methods are very applicable to those time series problems. Whereas, for example, in the C section, we have a lot of intermittent time series data where there's actually not much, there's actually no big non-linearity. It's most of the time very stable, and therefore some baseline methods actually, or some statistical methods, they do perform quite well. So you need to combine actually the best models together for different segments. And this can obviously be arbitrarily complex, since you have to define your segments first, and then also sometimes time series change from the one group to the other group. So there's lots of complexities that we have to deal with in here. So, for example, I took one additional example here. So what you see here is a time series for like a higher volume where you see some weekly patterns that are marked down here, but also within those weekly patterns you see some external drivers. For example, in this case, for example, there's a sales day happening, so you have multiple signals that are overlaying at the same time, and you need to find good solutions to cope with these kind of data situations. So what we do basically is, as I said in the beginning, we run different models on top of it. So for example, we could run a statistical model first. So statistical model normally is very good in fitting seasonal patterns. For example, here you see the weekly pattern is fit quite well, but for the external driver, for the sales day, the statistical model fails in order to model this nonlinear singularity. On the other hand, we have, for example, the machine learning models, where you can add external data, and you see here maybe that the normal seasonal pattern is not fit that quite well, but and also the sales day is overfitted a bit, but at least it picks up some distribution here. And what you can do is then to use AutoML methods to train all those models, and also at the same time ensemble the predictions that you get in the end for your final forecast. And this could then look something like this. When you combine the predictions, you get the best of both worlds of the statistics that are extracted and also out of the machine learning models that are driven by the external factors. And then by having multiple candidates of your ensemble, you get a much more robust prediction. And this is what we do internally automatically for all our customers that are there. There's one big question to that, and I think we all had this question in mind when training and hyperparameter optimizing models for our research. How long should I actually optimize? I mean, you can optimize arbitrarily long to maybe get those last percentages in accuracy. And most of the times it's also a question of time and money. But what the third key factor is sometimes, or most of the times, ignored, and this is what business value for the customer do I create with my optimization? How do I map my hyperparameter optimization, which is costly in time and money? How do I map this to actually a customer value, so I can explicitly decide how long to optimize for a better accuracy of my machine learning model? And yeah.
Yes, and I mean, that's when I would have been in the room, Robert, if you go to the next slide. Sorry, I think now I need to ask you every time. I would have asked how many of you, I mean, probably everyone minimum trained one model. We saw it also in the talk before, but how many of you really can map business impact and value to forecast accuracy. And what we see in the last years is that, especially when we go into companies, because I mean, this is an application industry talk, when we go into companies, there are a lot of people trying to improve accuracy. If you talk to decision makers, they cannot map it properly to the business impact. And that's a huge problem, because you might improve your model, but it doesn't matter. So I brought a little game. Robert, if you just flip to the next slides. As I always say, context matters. And that's a super simplified example, but it shows how the business world actually works, right? I say here I have two models, and perhaps I would like to understand, like, if you, I mean, they do different things, but if you would have to choose that you are allowed to use one of these models in productions to work with, could everyone perhaps in the room raise the hand who would go for model one? Robert, did somebody raise his hand?
I would say 85 to 90%.
Perfect. And if you click now again to the next slide, one more time, please. It really depends, because in this context, the second model is actually, I would go for the second model, because it just helps me to better detect a stock trend. If I'm over 50% right, I basically have an upside, versus the left one. I mean, it is really high in accuracy percentage, but I mean, it doesn't help the people that really have cancer, where you want to detect it early. This rate is probably way too low, because this model is good enough if it's always saying negative, right? And this happens a lot as well in industry. It's not that obvious, but people often say, oh, I have a metric, I want to optimize for this metric, and I want 93%, I want 95%, 99%. But often the metric they have doesn't relate really to the business context, and in this case actually is counterintuitive and not helpful in order to map or create valuable work when optimizing your model performance and accuracy. And that's why, if you jump to the next slide, Roman, we truly believe that optimization actually, so not only using optimization in an AutoML method and way to improve the accuracy, but also in order to model a business problem, to give some context, is key. Because as you can see here, everything Robert was talking about is this pink box, right? We have a prediction of future sales, but this prediction is only a small key part, actually, if you look at the business, because based on this prediction, a decision is triggered how much should be ordered per product, in this case, in order to fill stock, in order to minimize costs. Because, of course, if I order too much of a product, I have a lot of costs, because products I don't sell but are on stock just produce costs. But looking at the prediction now not only from a prediction perspective, but really saying, okay, now I have context. Now I know, okay, every percentage my prediction is better. I can better estimate how much to buy and therefore minimize my costs, is a total different game. And if you jump to the next slide, Robert, if we look closer, I just took one example now for one product. If we look closer now into the data, we see that, I mean, the pink line looking forward is the prediction, and all the other values are basically just calculated. So, but you get a clear recommendation, a clear number, okay, how much should I reorder based on the prediction in order to not run out of stock, but also have my costs minimal. So in this case, it's a really simple optimization. And you might ask yourself, but if you jump to the next slide, is prediction more or less the same as optimization? I would say in this context it is, but framing the problem as an optimization problem, even if the prediction is the biggest key part, a good prediction is the biggest key part in order to succeed and create value, it makes a big difference. And for us today, like, if there's one key message, like what did we learn on the hard way the last 3 to 5 years? It really matters to understand the context. It really matters to put more time understanding the context and framing the problem really as a business optimization problem before optimizing the predictions themselves. Of course, at the moment, this is not a really academic answer. I will go to this in a second, because of course we also want to quantify how much better is actually a prediction percentage, in order, like, how much should I improve and how much does it really affect my costs. And that's where we now get to multi-objective optimization. So super cool, it was also mentioned in the call before. Actually, almost no problem in this world is single objective, and if you try to weight the outcomes, you actually, there's a lot of valuable information which gets lost. So actually, if we look again at this problem, you will see there are some new blocks, and one of the new blocks is an outcome from the sales. It's the model uncertainty. So this is something based on backtesting and so on we can measure, and we need this uncertainty in order to calculate another target that we have, because availability. If we have SLAs, if we always want to have 99% availability or via SLA, it massively has an impact of how much we have to order. And it massively is based on the model uncertainty. If my model is 50% wrong all the time, I mean, I have to order so much more in order to keep my availability high. And therefore, just taking uncertainty within the problem as a next step really helps us to quantify what does this mean in the next step. How much uncertainty improvement or accuracy improvement does lead to how much cost savings and so on. And the result of this, now I take the model that Robert trained. Robert, I don't know, I assumed it looked like this model had a 84% accuracy. I was not sure what you're talking, but if you click one more time, so we see here now the outcome. Could you click one more time, Robert, please? Thanks, that's it. If you see the outcome, we see now here, Pareto's frontier, we saw already in the talk before. So we have the cost that we want to minimize, and at the same time, we have the availability that we want to maximize. And we see a beautiful Pareto frontier stating that there's an area between 300,000 and 400,000 where with each investment we really put our availability up, and afterwards it saturates. So this is all based on a model with the accuracy of 84%. Now, before we train a new model, as we have the accuracy as an input parameter, so we can just change this parameter, we rerun an optimization, and Robert, now just please jump to the next slide. We rerun an optimization and show the potential if we have a model included which has 87% accuracy, so improvement of 3%, how does the optimal scenarios or the Pareto frontier look like? And I mean, you can already see it's a jump, especially in the upper area. You probably can hit the 100% more or less availability, or at least the max, investing 300 to 400K less. But also for the other points, there's quite a gap. If you do this now for higher numbers, you will see, as Pareto principle state 80-20, you will see that often with going 88, 89, 90%, the jumps won't be that high anymore. And that's the great thing when we frame a prediction thing that we want to solve as an optimization problem and include the model uncertainties as a parameter that helps us to calculate based on SLAs, so service level agreements, how much we need from a thing, because then we also backwards engineer can do scenario testing and say, okay, how much improvement of a model quality affects my potential or shifts my Pareto optimal solutions in order to minimize more costs and to have more availability for less. And I mean, coming now back to the question Robert asked, if I have these clear numbers now, okay, I have availability, I want to go for this highest availability possible, I'm willing to pay the money. So I know, okay, I more or less save 300K. As a decision maker, it's clear for me to go for the improved to 87% route. But now everyone is aligned on why and that it has an impact. And it should be no problem also for us as researchers, as data scientists, to say, okay, there's a week of investment, we need bigger machines, we need to let it run longer in order to achieve this, but it's worth it. And I really would like again to highlight as the end of this talk, it really matters and it helps also for all discussions that we have. Always frame everything as an optimization, as a business problem, and try also, even in academia, try always to understand, okay, what does the thing that I do actually impact, and what is the thing that people are looking at, and how can I create a connection? If you can do this, you always can make quantified decisions like this by simulating, by really mapping data and your results into the thinking patterns of the people that make the decisions.
Yep, that's it. Thank you very much.
Okay, so we have time for questions. Do we have questions from the audience? Otherwise, I would have a question.
Mm-hmm.
Thank you. So, you mentioned very prominently that predictive accuracy is not all you need, but do you have ways to map the accuracy to the business value? Is that can you automatically do that, or is that something that you have to come up case by case, or that your customers have to provide you with?
Fabio, you got that question? I think this goes into your direction.
Sure. I mean, I can start, take over, Robert. I mean, there are patterns, but specifically you need to understand better the business problems. So for an industry, once you understood it, actually, I always say when people buy our product, they also buy a working process, because often people also in their daily work, when they do the work manually, they don't map these things. But definitely for an industry, you first need to really understand the mechanisms in order to map it in the right way.
Maybe I can follow up on what you said. I mean, we see that there are definitely patterns. So basically, as you can see here, this is causal graph that we put up here. It's like all these causalities, they do have like some constraints, and these constraints, of course, they are similar from one customer to the other. So we have this box of constraints that we can just put on or put off regarding what the customer is actually optimizing for. And so there are definitely similarities, and we can reuse those patterns. And obviously, but we have to turn them off or on for the given use case, depending on what the customer is actually optimizing for. So there are patterns, but obviously right now there is some human interaction in between to turn it off and on.
Thank you.
Well, on this one, I mean, I think like so the optimizing from the business, dollars essentially, that's probably possible only on small scale kind of businesses, like kind of large businesses. Say Amazon, for instance, like the downstream that will use the forecasting system will be as complex as the forecasting system, and probably way more complex. And complex in like the computational cost just to run this thing. And so I think there is a limit at some point where you have to say your forecasting system is measurable accuracy, and then the downstream system has to use it the best it can, but you can't really have a unified system for it.
Yeah. Fabian, did you get a question?
I think so. So what is interesting, I mean, this looks complicated and computationally expensive, but if you remember the meme prediction looking at optimization and being the same, often it's just like a calculus that is normally done in Excel. So it's really, I would consider it as a post-processing step in most of the cases, if you just want to map it, which is really inexpensive and also scalable.
Are there more questions? I have a question. So, because the talk was called Multiobjective, right?
I didn't quite understand the multi-objectivity. And another question following this, like you showed univariate time series, right? Do you do multivariate time series as well?
Yeah. So first of all, the first question was where does the multi-objective optimization comes in here? I would then answer your second question first, if this is okay. Yes. So we also work with multivariate time series as well. So we basically we have a framework that you can where you can input and introduce all kinds of different features at the same time for your multivariate approach. And so this is one of our key, I would say, when Fabi is saying you buy a working unit, so obviously these data is not standardized by the customer. For example, different data sources drive different businesses. So we see, for example, in the e-commerce business, obviously, they are driven by the sales days, some action days that are put online, whereas other businesses are more impacted by holidays or public holidays and all that stuff. So especially for the sales day of part, it's hard to gather them in the beginning since it's completely not standardized, and there is currently some pre-processing involved in every use case. But in the end, it pays off since these, especially those sales days, they have a big influence on outliers. So if you want to get rid of the outliers, which are most of the time the most important factors for actually for the demand forecasts, you need to do this front-up work in order to include all those different information for the time series itself. Yeah. And then the first question was, Fabian, where does the multi-objective comes in?
Yeah, we start this presentation with another spin when you created it. So we first want to do the trade-off really cost versus accuracy in the solution space. That you really see the trade-off between model uncertainty or model accuracy, if you turn around, and the business value. But while creating this story, we changed a bit. So that's why it might not 100% reflect the title, because we thought showing a multi-objective problem and then showing the uncertainty, which is rather not an active input, right, but a use case parameter, which we cannot change within one optimization run, would be super interesting to see the different potentials within a two or more dimensional space. When you improve the accuracy. So it was just when we had the title of the talk and when we refined the things, it was matching better from the storyline like this.
May I ask you a follow-up?
I'm really sorry. I have to jump out because I have a customer call since 2 minutes. But Robert can give you my email address, and we can for sure jump on a follow-up if you want. Super happy to connect.
Thank you, Fabi. Bye-bye.
So do you integrate the pre-processing into the AutoML? Or is it like really a human design pre-processing?
So partially, so it's both actually in the end. So there is definitely some human layer right in the beginning from the customer raw data, because the customer raw data is you can reuse some standard steps in the pre-processing, so they all kind of look alike, but in the end they have very, very custom ways of how they give us their data. So this first pre-processing step is definitely human layer, but then we have obviously pre-processing steps talking about data scaling, data transformations, data normalization, and also data enrichment, which is all automated and which is part of the automated pipeline. So there is like this first human layer, and as soon as we have it in a standard kind of format, then from that point in time, it's all automated and there's no human intervention included anymore.
So your pipeline would automatically choose either interpolation, imputation, or something like a GAN?
Yes. So yeah, this is all included in the optimization process itself. Yes.
A short question. Do you only work with text data or tabular data, or do you have other modalities as well?
we have all modalities. So we have tabular data modalities that are applicable for certain problems and for certain data that we see. We, on the other hand, also have sequential model families, MLP-based, transformer-based. It's all included in the AutoML process itself, as well as the statistical models. I mean, this is kind of tabular, but yeah, so they are all included. So from the whole model zoo, we train them and we also combine them. And I think this is what I try to express beginning of the talk deck. These models, they do have certain strengths in certain areas. We try, I mean, we can have another talk completely about ensembling now, but there are so many ensembling strategies that are coming up and they provide value. Talking, for example, about right now, the assembling mostly takes place on historical values. So you have a hold our test data set where you calculate your metrics and then you assemble on top of that. But maybe next month is a sales day for one certain segment. And then the whole dynamics of the time series changes and suddenly like a low volume time series suddenly becomes a high time series. How do you incorporate that? Since if the dynamics change and there's a data drift, also the ensembling needs to change accordingly. So these are like problems that we need to solve, and this is like a research topic at the moment for us. We're not done there, so I can't give you a full-fledged talk on that, but just can explain you the tendencies where we're working towards to at the moment.
Good. Then let's thank the speaker again.